Hi everyone, my name is Abdurrahim bin Muhammad Azid. I will present to you about introduction. For this slide, I want to ask you a quick question. How many of you think hardness and hardenability are the exact same things? Well, you are not alone. But today, I am going to show you what that's a total myth. Think of it this way. Hardness is just about how to the surface it, like a shield. But hardenability, that is the real MVP, is the still ability to transform into martensite deep down into its core when we cool it down. It's all about the depth of the strength, driven by the cooling rate and the secret sauce of its chemical mix. Understanding this is basically our superpower for picking the right material for heavy duty engineering. So let's dive in. Let's go.
Assalamualaikum. My name is Danish bin Fakirul Azila. My matrix number CD250096. So for the experimental equipment, we need to prepare our equipment, which is standard steel specimen that has been heat treated, and we need to prepare our Vickers hardness tester, which is for hardness ability test. So for the experimental procedure, first the specimen was grounded along to obtain a flat surface, which is we need to grind our specimen. We need to grind our specimen to get a flat surface to get the accurate reading. And then the sample was clamped at Vickers hardness tester, which is our equipment. And then the load 50 kilogram force. And then the microscope was then adjusted by observing the two parallel measuring lines. The lines were moved until the both lines overlap exactly, which is it will be one line. And we need to press the reset button. And for this step, we only doing this only once before you proceed to the next step. And then the indenter was turned front. The specimen was moved up until the bit touched the specimen, and then we need to press the start button and left until the light turn off. So for the next step, the stage was moved down, and we need to change the bit with the microscope to the center, which is we need to turn the microscope until it sounds thick, and it was to look through it. And we need to move the stage up until we see the diamond shape sign. And then to do the measurement, we need to align the both line to touch the edges of the diamond shape, which is we need to touch the edges of the diamond shape to this line and this line. And then we need to press the read button, and the reading will appear at the machine, and the reading will at each 1.5 to 2 mm. At least 15 readings were taken to plot the hardenability curve, and we recorded our reading in table 3.1.
Hi, my name is Ahmad Amir Ashraf bin Ahmad Mazani. My metric number is DD22005. I'll be presenting result. Okay, for table 3.1 present that Hardness measurement recorded at incremental distance from the quench end and Gemini specimen. The data indicates that the highest hardness occurs at the quench end, where the specimen is immediate contact with the quenchant. This is due to the rapid cooling in this region, which promotes the formation of harder microstructures such as martensite. At the distance from the quench end increases, there is a gradual decline in hardness. This trend corresponds to decreasing cooling rate along the length of the specimen, resulting in the formation of softer microstructures such as bainite and perlite. The hardness gradient observed across the specimen demonstrate the direct relationship between cooling rate and material hardness, highlighting how thermal treatment affect the mechanical properties of steel. For this slide, the relationship between cooling rate and material properties is clearly illustrated in the hardenability graph, where hardness in HV is plotted on the y-axis and distance in millimeters from the quench end, and on the y-axis. The graph shows a distinct downward trend in hardness as we move away from the quenched end. At the quenched end, the specimen is direct contact with water, resulting in an extremely rapid cooling rate. The rapid cooling promotes the formation of hard martensitic macrostructures, which is reflected in the peak hardness observed at this point. Moving further along the specimen, the cooling rate decreases, allowing the formation of softer microstructure such as bainite and perlite, which correspond to the gradual reduction in hardness along the bar. Overall, this graph provides a clear visual representation of how cooling rate directly influence the microstructure and hardness of steel, highlighting the critical role of quenching in controlling mechanical properties. The indentation analysis, the indentation size increase as the distance from row. Near quench and tip, the indentations are minimal, indicating the material's peak hardness. Further away from the quench end, larger indication are observed, reflecting the gradual decrease in hardness along the specimen. Next is microstructural gradient. At the quench end, rapid cooling product produce a hard martensitic microstructure. This high cooling rate locks in a dense and rigid structure, which directly contributes to the peak hardness observed in the region. Lastly is phase transformation. Region farther sorry, region farther from the quench end cool more slowly, which allows softer microstructure such as perlite and ferrite to form. The progressive change in microstructure along the specimen illustrate how the cooling rate govern the mechanical properties, creating a distinct gradient from hard, martensite, and softer phases. That's all from me. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Today I will be presenting our discussion on the hardenability of steel and the factor that influence its mechanical properties. Okay, for the A is discuss the hardenability curve and explain the relationship between hardness and distance from the quenches end. Okay, for the is first the hardenability curve show a clear decline in hardness as the distance from the quench end increases. This occurs because the cooling rate is slower further away from the water source, and the slower cooling allow for the formation of soft perlite and ferrite, whereas the fast cooling at the tips create and hard martensite. Okay, for the B, the factor that influence the hardenability curve is Several key factors determine the shape of this curve, including the presence of alloying element and the austenitizing temperature and time. Other other critical factors are grain size and the overall cooling rate, which is determined by the specimen size and the quenching mediums used. Okay, C. Discuss the difference in hardenability curve between water and oil quenching at the same temperature. Okay, when comparing medium water quenching produce or significantly steeper curve due to its high thermal conductivity, promoting and maximum maintenance hardness. Okay, in contrast, oil quenching result in a gentler slope and lower peak hardness because its lower cooling speed lead to barytic or pearlitic microstructure. Okay, 4D is a cylinder bound with 25 millimeter diameter and 100 millimeter long is a alternate size in a furnace followed by quenching in a still water. If the entire specimen is immersed at the same time, predict the hardness versus distance from end quenching curve. Uh, the if a specimen is fully immersed in water all at once, the cooling rate become uniform along its entire length. This eliminated the diastatic hardness drop seen in a Jomini test, resulting in a horizontal hardness curve with the consistent property from one end to the other.
Okay, guys, we have arrived to conclusion for this project, for this lab. In conclusion, our study on steel hardenability was successful, complete using the Gemini and quench procedure. From our observation, there is a clear connection between the cooling rate and the material hardness. At the quench and we where the cooling is fast, we we obtain a martensitic structure. We provide the highest hardness. However, as we move further away from the water, the cooling rate decreases and the steel becomes softer. This test clearly prove how cooling conditions govern the hardness distribution throughout the material. Therefore, understanding this correlation is vital for choosing the right heat treatment in engineering. Okay, that is all. That's all for our presentation. Thank you for your time. All right. Thank you guys. Bye.